Thank you. Our next distinguished lecturer is Professor AHMED ABDRABOU, Assistant Professor of Radiology at Ain Shams University in Cairo. Prior distinctions include work as a consultant radiologist at King Fahd Armed Forces Hospital in Saudi Arabia. Thank you.
Thank you for your introduction, and thank you, Conference Committee, for having me today. Good afternoon, everyone. Our topic will be about diffusion and diffusion tensor imaging and tractography. Water molecules move randomly in temperature more than 273 below zero, which is called Brownian movement. And in 1965, two scientists introduced a new sequence that is sensitive to Brownian movement by the application of two motion-sensitive gradients to MRI pulse. And we know that diffusion weighted image represents the in vivo observation of the diffusion process. So if we observe this molecule of water, after a while it will move to this location, and we can represent this movement by a vector like this. Another molecule will move to another location, and more molecules we can see, and they move randomly in this space. And we can represent this movement by a circle, which means that this diffusion has no preferred direction, but it is free. So any molecule of water can move anywhere inside this circle at a certain moment. We call this type of diffusion isotropic diffusion. An example of isotropic diffusion is the extracellular space, where you can find the molecule of waters can move freely between the cells. This is different when we deal with something tubular like white matter fibers, okay? Because the molecule of water here can move after a certain amount of time to this location, and now we can represent this movement along the direction of the nerve fiber. It's more preferable along the direction than perpendicular to the nerve fiber, and we can represent it as an oval-shaped ellipsoid. And we call this type an isotropic diffusion. So we have now a circle which represents the isotropic type of diffusion, an oval-shaped and isotropic type of diffusion, and the narrower this oval shape, we have more and more anisotropy, and this is actually what's happening inside the nerve fibers. And we know that this anisotropy has a high fractional anisotropy value and low ADC value, which is normal for the nerve fibers, while in case of isotropic diffusion, there is low FA value and high ADC value, okay? And we know that the nerve fiber which changes from the anisotropy to the isotropy is abnormal. And this occurs with certain diseases, like, for example, demyelination. So this is diffusion. Where the word tensor comes from? Actually, when we represent the movement of the water molecule, it's in a 3D space. So this red arrow represents the movement of the water molecule, which is actually the ellipsoid, the diffusion ellipsoid. And to describe this movement, we have to plot it against the x and the y and the z. And so we will get a dxx, dxy, dxz, and dyx, dyyy, and dyz, and dzx, dzy, and dzz. And this matrix is called tensor. So what is tensor? Tensor is a mathematical representation of the water molecular movement. So to recap, we have a diffusion which is free in cases of isotropy, no preferred direction, and anisotropy, there is a preferred direction. And we have a restricted diffusion, which is always pathological. So when a patient introduced inside the MRI machine, and for example in a 1.5T machine, we know that the protons will be magnetized. And when you apply a 90-degree pulse, we know that these protons will be aligned together and in phase, and this will produce signal. Now we will apply the gradient, and the gradient means that the field is not homogeneous. So we have a high end at one side and a lower end at the contralateral or the other side. And the proton who will exposed to high end gradient will move faster, while the proton in the lower end of the gradient will move slower. And now they are not in phase, and we will cause signal loss. Apply again a 180-degree pulse. Still, the fast proton will move fast, and the slow proton will move slow. So you still have an out of phase condition, and we have signal loss. But when you apply the other gradient in the other direction, so the slow proton will be exposed to a high field gradient, so it will move faster, and the fast proton will slow down, and they will come together and become in phase, and you will have signal. So when you apply the next gradient or the second gradient, you will have signal. But actually, this signal is also expressed for only the static protons. So what happened when these protons move? So if the proton moves between the first and the second gradient, and he, for example, this green proton, he was exposed to a high gradient, okay, so it moved faster, and then he turned it to the other side of the gradient in the second gradient, and it's still faster, so you don't have a signal, you don't have in phase condition. The slow proton, the red one, was exposed to a lower gradient, okay, and when he moved to the next gradient, it's still low. So there is a out of phase condition, and you have signal loss. And this occurs when the protons moves from one gradient to the other gradient along the direction of this gradient. So it's a fact that diffusion causes signal loss. And this is rule number 1. So the water molecule moves along the direction of the gradient will lose signal, while other static or water molecules that moves perpendicular to the direction will gain some signal. So let's apply this. If you in this gradient, if you look at this gradient, you will find that the fibers in the anterior thalamic radiation here is low signal, while the fiber in the corticospinal tract is bright, and the splenium of the corpus callosum is also bright. So we conclude that the diffusion of gradient is applied in an anteroposterior direction. That's why this fiber lose its signal. Another image here, you can see that the signal loss occur along the genu of the corpus callosum and the splenium of the corpus callosum as well, while other fibers are still high signal. So we know that the gradient direction is from right to left or left to right. And this image, you can see the signal loss occur at the corticospinal tract, posterior limb of the internal capsule, while other fibers still have some signal. So this is a craniocaudal direction of the gradient. So when we combined all the direction of the gradient, we finally get this image, which is the diffusion image we get from the MR machine. During practice, we do what is called the p-value, which is the sensitivity of the gradient. It's we do it in at least three parameters, P0 and B500 and B1000. And we fed the computer with all this data, and it creates what is called ADC map, like this one here, okay? And when we apply the direction, not only the diffusion, but the diffusion and the direction also, we get what is called FA map, or fractional anisotropy map. And because we apply the direction here, you can distinguish between the gray matter, which is black or grayish like this, and the white matter, which is hyper intense signal. There is very clear distinction between both. And when you apply the direction, in every direction will be coded like in color map. So you have what is called color FA map, and this map represents the direction of the fiber. So for example, a green fiber means that the direction is anteroposterior or posterior-anterior. A red fiber means that it is right to left or left to right, and blue fiber means craniocaudal or caudocranial direction. And in this color map, if we magnify a small part of this map, we will find that it contains hundreds and thousands of what is called diffusion ellipsoid. So this diffusion ellipsoid actually represents the water molecular movement. It's just what we have represented before as an oval-shaped ellipsoid. Yes, this oval is shaped ellipsoid for each pixel of the matrix. And when we combine these ellipsoids together, we will create what is called tract. So a tract is just a combination of thousands of small diffusion ellipsoid inside the matrix. And here an example of an arcuate fasciculus which connects the Broca's and Wernicke area in the language pathway. And here an example of a case of hemangiopericytoma in which this large lesion caused displacement of the inferior occipitofrontal fasciculus, as you can see here, and also make a separation between the nerve fibers. So what is mechanism of diffusion restriction? So we have cells and we have extracellular spaces, okay? So if the cells ballooned and enlarged, it will cause a restriction of the extracellular space, and this causes diffusion restriction. So you need to do a diffusion restriction to fill the extracellular space. You can fill the extracellular space by increasing the size of the cell itself. And this is the typical what happened during infarction. So in infarction, the cells will lack of glucose from cutting the blood supply, and the sodium-potassium pump will dysfunction. And so the sodium get inside the cell again along with the water molecules, so the cell balloons, and when the cell balloons, they restrict the extracellular medium and cause diffusion restriction. The other mechanism of diffusion restriction is keeping the number of the cells as it is, but the size of the cell as it is, but increasing the number of cells. So for example, you have the same size of cells, but they becomes many and many, so these many cells restrict the extracellular space and cause diffusion restriction. And this typically occurs with some tumors. We call it a highly cellular tumor or cell-packed tumors, like for example here, medulloblastima, which is here in the brainstem and causing diffusion restriction in the ADC map. Another pathology that use this type of diffusion restriction is abscess, because the medium here is now filled with cellular spaces, inflammatory cells and macrophages and things like this, which also restrict the extracellular space. An artifact for this is what is called the T2 shine-through effect, which is you see a high signal in diffusion and also high signal in ADC, so it is not a diffusion restriction, okay, because diffusion restriction, a high signal in diffusion should be low in ADC. That's why you should look at another map. It's called exponential ADC. And exponential ADC is used to distinguish between actual diffusion restriction from a T2 shine-through. As you can see here, high signal in diffusion, high signal in ADC, and low signal in exponential ADC. So this is rule number 2. If you have a hyperintensity in the DWI and low intensity in ADC, you are dealing with true diffusion restriction. On the other hand, if you have a high DWI and high ADC, you are dealing with T2 shine-through. So there is a quantitative measure also in DTI in which we can measure what is called FA value, which is fractional anisotropy value, and also ADC value to get mathematical measures of the diffusion restriction. And this is an example of ROI, which was put inside the brain, and we can conclude that there is some measurements. These measurements is ADC and FA values. So take-home message is a free diffusion can be without specific direction, it's called isotropy, and or with specific direction, it's called anisotropy, which is normally in brain fibers. Restricted diffusion is always pathologically. The more diffusion occurs, the more signal loss, and only interpret DWI image with ADC map. Thank you for your listening.
Thank you, Dr. Ahmed, for his excellent talk, and I think that it is a hard subject, and he try as